Okay, so in this module, I will focus on MRC and ANOVA, which are both forms of the GLM. So here I provided the equation of the GLM, which is essentially the observed equals our predicted plus the residual. Specifically, our dependent variable is equal to the y-intercept, or b-naught, plus the weights of our predictor times the matrix of predictors, and this is because we can have more than one predictor, plus our error, or our residual. We assign each of our predictors a weight to help us better understand why, and this model is linear because it is additive, as you can see in the equation with the plus signs. So though they are both part of the same model, in MRC we are testing regression parameters, whereas in ANOVA we are testing the difference between classes. So first I'm going to focus on the MRC, and MRC is a measure of association that allows us to look at more than one predictor. I conducted MRC in SPSS with 3 predictors, x1, x2, and x3, and 1 outcome variable, y1. MRC is all about parameter estimating. In this coefficients table, I pointed out the parameter estimates of the model, which are our B's. Our B's are our weights in our regression coefficients, and they tell us how relevant our predictors are in helping us understand why. So our B's divided by the standard error give us the t-value. We use the t-value to determine if our predictors are significant. So as you can see here, it looks like we have insignificant predictors because they are all above the set alpha of p is less than 0.05. Our goal in MRC is to select a straight line that minimizes the sum of squares of the parameter estimates. So we compute the line of best fit with the least amount of error by computing the least squares estimates of the regression coefficient. So this is our R-squared term, and the R-squared tells us how powerful of a predictor our model is of our outcome by telling us how well our regression line accounts for the variation of the dependent variable. So in this model summary, the R-square value for our model is 0.344, and really the closer our R-square is to 1, the stronger our model is at predicting our outcome variable. So here I would say that our model is not very strong at predicting our outcome variable, and this is consistent with the significance or lack thereof in the coefficients table. So yes, we do not have a strong model, and we fail to reject the null. So I'm going to go over some diagnostics and assumptions of MRC. Diagnostics are important because they help us assess the relationship between the observed and the residuals. So first I'm going to talk about rectilinearity. MRC assumes that the relationship between x and y is rectilinear, or that there will be a straight line in the relationship between the predictors and the outcome variable. So I created a matrix analyzing the relationship between each of the 3 predictors and the outcome variable, which is y1. Based on these 3 scatter plots, I can assume we have rectilinearity of the relationship between x1 and y1, as well as x2 and y1. However, there are some points of concern over here, and also x3 and y1 is a rectilinear relationship. However, there are some points of concern over here, but overall this is we do meet this assumption of rectilinearity. Moving on to multicollinearity. Multicollinearity is about the relationship between the predictors. So we do not want our predictors to correlate because the correlation will interfere with the ability to detect causality. So first, if you look at the correlation matrix table, I ran correlations between the predictors to see if I would see any trends of correlation. So it looks like x1 and x3 do seem to correlate here. And then I also computed the variance inflation factor to see if any of the predictors correlated. And essentially, the closer the VIF is to 2, the more concern you have for multicollinearity. And as you can see, x1 and x3 are fairly close to 2 at 1.84 and 1.835. So I would say we have an issue in multicollinearity here, and we do not meet this assumption. Moving on to independent residuals, the MRC also assumes that the residuals will not correlate with the predictors. So we can compute the Durbin-Watson to assess this assumption. So if the value is close to 2, we can assume that the assumption is met, or the closer to, the more likely that the assumption is met. So here we have 2.076 for our Durbin-Watson, which I would conclude is close to 2. So I would say that we meet this assumption here. So moving on to influential outliers, I created a box and whisker plot to see if I had any outliers in the variables, and as you can see, x1 and x2 both have outliers. So then I wanted to see if these outliers had any influence in our model's predicted how well our model predicts our outcome. So I computed Cook's distance, and as you can see, if you look at the minimum and the maximum of Cook's distance, all of our values fall within -1 and 1, so I would assume that none of these outliers are influential in our data. So to assess if our residuals are normally distributed, I computed a PP plot, and here we can expect that our residual values will fit on a normally distributed line. We would be concerned if there was an S shape of the residuals. However, from looking at this plot, I would say that the residuals are normally distributed. So I also created a histogram to assess normally distributed residuals, and based off of this, it looks like our residuals all pretty much fit within this normal curve, normal distribution. So this assumption is met. So homoscedasticity, we are testing the assumption that there's no significant deviations of our residuals. So by looking at this plot, we want our residuals to be constant for all values of x. There are a few points here that seem to be an issue, like over here. But overall, I would say that our residuals are constant across the unstandardized predicted value. So I would conclude that we do have homoscedasticity and that this assumption is met. So now I'm going to move on to talk about ANOVA. So in ANOVA, we are testing the difference between classes. So the classes that I looked at are F1 and F6. We want to see a significant difference between these two classes. So our mean squares are the sum of squares divided by the degrees of freedom, and it's essentially our signal over noise or a variance. So the F value is the ratio of variances, which we get by dividing the mean square between groups by the mean square within groups. And the F statistic is our parameter estimate. So the F statistic and the degrees of freedom give us our p-value, which we use here to determine if we can reject the null. So here we have no significant p-values because they're all over the alpha of p is less than 0.05. So we fail to reject the null. And we do not see a difference in these means. So if I had significant results in running in ANOVA, I would have to run a post hoc test to determine where the difference in the means lie, because ANOVA itself only reports omnibus findings. So since I did not find any significant results, I didn't conduct any post hoc tests, but two common ones that are often used are the Bonferroni and the Tukey. So as you can see here, we have an unbalanced design because there's a disproportionate amount of subjects in the groups, where F1 has 16 subjects and F6 has 15. So this assumption is important because ANOVA does not know what to do with the degrees of freedom in unbalanced designs, which makes the results somewhat uninterpretable. MRC, on the other hand, is more flexible and is better at accounting for unbalanced designs than ANOVA is. So despite this being a pretty major issue in analyzing our results, I'm still going to talk about some of the assumptions and the diagnostics in ANOVA. So I computed the Levene's test of equal variances to see if I had identically distributed errors. So since there's no significance at 0.413, we can conclude that I do not have, I do in fact have homogeneity of variance, so this assumption is met. Moving on to normal error distribution, I created a QQ plot to look at the distribution of error. The error terms here look to be normally distributed around the observed values, so this assumption is met. So to assess whether I have homoscedasticity, on the provided correlation matrix, I'm going to look specifically at the predicted on the x-axis and the standard residual on the y-axis. So here it looks like, for the most part, the error is consistently distributed across the predicted value. Apart from the end here, it looks like there may be some points that aren't, but overall I would say that we do have homoscedasticity and this assumption is met. So now I'm going to talk about some similarities and differences of MRC and ANOVA. So they're both a part of the GLM because they are both linear additive models. So some similarities are they both have the same assumptions, so we're assuming independent errors, identically distributed errors, and the distribution of error is normal. So they also both assume that there are continuous dependent variables. So as pointed out In Cortina 2002, often researchers are ignorant about this assumption. If we include dichotomous variables, we violate the assumption of normally distributed errors as well as homoscedasticity, and have useless test statistics. So also, as King 1986 notes, we need to use other nonlinear models when we have dichotomous dependent variables like a logit or a profit. So they also have similar hypothesis tests in that they both report omnibus and simple effects of predictors. However, in ANOVA, as I mentioned earlier, you have to run post hoc tests in order to determine if there are simple effects. The residuals are additive, and again, this is because they're both part of the GLM, which is restricted to an additive model. And then finally, they both focus on variance. So in ANOVA, the F statistic is a ratio of variances of our mean squares, and in MRC, we are testing to see how well our regression coefficients can account for variance in our dependent variable. So there are some differences. In ANOVA, our predictors are class factors, whereas in MRC, they are covariates. So in ANOVA, we are interested in mean comparisons, so we extract covariance from our model. In regards to diagnostics, in MRC, we attribute residuals to the model specification, whereas in ANOVA, we attribute residuals to the population. So in ANOVA, residuals are viewed as error, since we assume that we have a perfect model. But in MRC, we're interested in these deviations because we attribute them to problems with our model. In MRC, we look at individuals, whereas in ANOVA, we look at how individuals contribute to the group. So in my software analysis, I ran two factors for ANOVA, which were F1 and F6, that looked at these two different groups. And in MRC, I looked at the three different variables, X1, X2, and X3. So the GLM is a single model because you can take one measure and convert it to the other using the point biserial correlation. So we can convert a T into a measure of association by using this point biserial correlation. And essentially, we take the square root of the T squared divided by the T squared plus the degrees of freedom. So as you can see here, the significance of a test is really the function of the size of the effect and the size of the study. So the formula essentially shows that MRC and ANOVA are a part of the same family because they share common terms. So that's all I have for Module 3, and I'm going to now show my hand calculations. That is it. Thank you.